record. So just a couple of announcements. Test number 2 will be next Wednesday, November 3rd at 5 p.m. to 6:15. For those who want to opt in so that test 1 results are counted towards the midterm, they have to send me an email to say that they want to opt in by before that, so by Tuesday sometime, all right? And then I just found out today that the final for our 204 is on December 15th, Wednesday at 6 o'clock to 8:15 p.m. You got it? It's 6 p.m. to 8:15 p.m. And the room most likely would be MR3, but that is up to somebody else in the registrar office to assign. So for the moment, the room is to be announced, but it will be live. Okay? And then test 3 is on, oh, I should look at the calendar, November, whatever, the Monday of that Thanksgiving week. Because if it were Wednesday, it's too late because Thursday is Thanksgiving. So I have to set it for Monday, whatever that Monday of the Thanksgiving week at 5 p.m. All right. Any questions, or did I make all the necessary announcements? I will have to update the syllabus. I better remember because all these things keep changing. So I will update the syllabus hopefully sometime later after the class. Any other questions? Yeah, that's right. So it's November 22nd. You're right. Right. It's the Monday, November 22nd. Right. That's correct. All right. Any other questions or comments? Yeah, I make the lab count, but I have to also work with the lab TAs to settle all these. But yes, because there will be the final week, the lab, I guess the supervisor will set up a schedule for makeup labs. If you did not attend any lab, there is a makeup lab, but then you have to sign up for it and it gets very complicated how they schedule it. So I don't know, given the situation, but that is still on the calendar. As to when that makeup lab schedule is, I don't quite know. Maybe it's the same week of the final. That's something beyond my understanding or control. Okay. All right. Somebody else has. Yes, the final will be sort of cumulative, but more, I guess, it depends. As we get there, we will have a better sense, but it will be sort of cumulative, but more from you know, weighted towards the later part. Okay. All right. Now we better kind of like finish the electromagnetic waves, because as I saw the lab schedule, I think this week already you're starting on optics, which we hopefully we can cover optics. Although the optics we'll be covering is elementary optics, because you're not going to be a real optician. You're not going to be in the engineering aspect, but nonetheless, there are many things that you already know about optics imaging. Okay, so now let's oh, before we begin, I also want to point out, you remember the Wiley Plus, their slide, they actually had an extra term, so I have now put an X on that so that if you follow through their thing, it does give you the correct answer, right? But that's when I upload the PowerPoint, you will see. Those are the little things that you have to be careful about. All right, so now we want to now deal with a very important aspect of the electromagnetic wave that comes from the sun, that comes from later on towards the end, we have the electromagnetic wave that comes from the butterfly or that comes from the wall. And the electromagnetic waves that come, they are all not polarized. That means that the electric field, there are some of the electromagnetic wave, where the electric field is, let's say, oscillating in the y direction, with the magnetic field oscillating in the z direction, so that you are propagating in the x direction. But the orientation of that is random. So for a light that comes from the sun, it is really randomized, so it is not polarized at all. But now we want to have a way of looking at special orientations, and that's where we have polarizer, or in the old days they call it a Polaroid lens. There used to be a company that's very big called Polaroid, but they after a while everybody else knows how to make Polaroid, so now there is no such company called Polaroid, but the technology is there. And what you really do is you have whatever is your unpolarized light coming in, and you have a filter that only lets the light whose electric field is going, let's say, up and down, to come through. And this is sort of like an example of a rope, and you have a vertical rope oscillation, and it will be able to come through. But if your polarizer were oriented perpendicular to it, this wave would not be able to come through. So this is what a polarizer is. And now we are not going to go into the actual physics behind how do I make a polarizer so that it will only let electric waves that are oscillating in the y direction to come through. That you leave it to the scientists. What we now as a user, we just say, well, sometimes there are good reasons why I want to only let those light that are polarized in one special direction to come through. You know why? Because out here, there's a glare. The sunlight, it has the light that is of all orientations, but it is too much for my eye. So I have a sunglass. What does the sunglass do? The sunglass has a polarizing filter, and it filters out so that only this orientation comes through. And generally, you can sense that that would be much less intense than the original one. The original one has orientation all over, but I only see that portion of the light that comes through according to my orientation of my polarization. All right, so this is what we will be talking about, polarized light. And this says that if I have a wave travel and I have a light that is polarized, then my electric field that came through all will be just simply oscillating in the y direction, let us say. Whereas if it is not polarized, then of course it's all over. All right. And polarized light may be produced from an unpolarized light by a polarizing material, by a filter. The book calls it polarizing material, but I would call it a Polaroid filter, so that those other orientations don't come through, only this orientation comes through. So I now will be able to see only this much. And generally, if I have light intensity of whatever is the intensity, so many watt per meter squared. If I have this much intensity with a filter, I only get half of it. Because on the whole, it is like when I have randomized it, it's like I have half of it this way, half of it this way, but spread all over, but half of it this way, half of it this way. So when you now filter it, what I get, my intensity afterwards is half. And I wear a sunglass in order to cut down on the intensity. Okay? And now what they now, and this is sort of a little bit more technical, but just to recognize it, if I have unpolarized light and I have a polarizer, a filter, and I only filtered so that only those that are vertical, let's say in the y-axis, then when it comes out, they will all be oscillating this way. But then I have another, which they call analyzer. In other words, you now want to be like a scientist. You now want to sort of like, and actually even as a child, you want to have fun with it. If you already have a sunglass that filters out so that it all comes in the y direction, then I have another filter. And what I want to do is now say, hey, what if I now take the filter and I twist it, I rotate it, instead of now enabling the waves that are vertical oscillation in the y direction, I will now insist only if you are sideways, let's say in this direction, I will let you through. Well, what happens is that then there will be less that comes through. How much less? Well, what they now say is, I look at the electric field. I made sure that all the electric field coming was here, in this direction. But now you insist, because you have another filter, you have an analyzer, they call it, because they are a scientist, then only the component of this electric field that is in this direction will come through. You follow what they're saying? You look at this vector. The electric field, they are going this way. But as a vector, it has a component that is in the direction of your new filter, and that direction is now cosine of this angle. And so then the amount that comes through is now less. Why? Because the electric field strength that comes through is less. And there is this, I don't know who is this Malus, because I'm not an engineer. This Malus has now figured it out and say that therefore the resultant intensity that you measure is cosine squared theta, because the strength, you remember, the energy of the wave that comes through depends on the square of the electric field or the square of the magnetic field, and the magnitude strength of E and B are the same for electromagnetic wave traveling through space. So since only this component of the electric field can come through my new orientation of this analyzer, then the intensity that comes out is now cosine squared theta, and that is Malus' law. And the book here now says, this was the intensity before the analyzer, this is the intensity after the analyzer, and that's the cosine squared theta. You're not going to be tested on this. It's the kind of common intuition that you have, that if I have a Polaroid that is oriented this way, and I now have another Polaroid that is oriented a little bit this way, then originally I got intense, then the intensity gets less and less and less and less until my new Polaroid direction is perpendicular to it, I get zero. I get dark. I don't see anything. Well, this is just the same. And then this is really just for engineers. What value would it be so that my the intensity of light that comes here is now 1/10 of the original intensity? Well, that's just making use of cosine squared theta. So we will quickly go through this. You're not going to be tested on this, don't worry. This is now the intensity of the polarized light, because you already know you get half. Well, then the intensity out here is now whatever is the intensity before you filtered it, times cosine squared theta, where theta is the angle. And they say you want this intensity to be 1/10 of the original unpolarized light. And you can now work it out. You say, therefore, this says that cosine squared theta is 1/5, cosine theta is this, and therefore angle is 63.4. But you're not engineer, I'm not engineer. We already have a sense of the understanding that as you give me polarized sunglass, and if you now orient the second one, as you vary it, the intensity gets less and less and less and less until when you are 90 degrees, it is 0. Well, this shows. Here is my polarized sunglass, right? And if I now, and I have two sunglasses, right? So the light that comes through the first one is polarized in whichever direction, let's say in this direction. Then I take my other sunglass, which also is polarized in the same direction, because you need to wear wear glasses that the left and the right have the same polarization. And now if you now take the second pair and you rotate it, not twist it, you rotate it. If you rotate it such that it is now 90 degrees, it's dark. No light comes through. So that is what we were faced with in the earlier situation. All right, this is just the practical fun you have with sunglasses. Have you ever played with sunglasses? Does anybody wear sunglasses?
Yes.
Yeah. And there is a difference, right? When you wear a sunglass, it's less glare, right? You must have. So this is basic principle in the sunglasses. Well, the basic principle for 3D, IMAX. Does people go to IMAX these days? Yeah. Now, do you like wearing those glasses? In order to see a 3D movie, you have to wear their glasses, right? Yeah. And you know what happens is you have your, I guess, the left eye and the right eye, and the polarization of the left eye and right eye is purposely made a little bit different, so that what you see with the left eye are those that are, let's say, polarized this way, and those you see with the right eye is maybe polarized, I don't know, some at an angle. I'm not in the industry, so I don't know. But the people who make this 3D glasses, they make sure that it is in a particular direction. Why? Because it has to be the same kind of orientation as the original camera. Because for the 3D, they have to also go and shoot the, scene of the eagle flying, and the camera will have also two lenses. And what you now see with your left eye is what the left lens saw, and what you see with the right eye is what the right lens saw. And then it will be like as if you are there and you see the original thing. If you don't wear, then what you see on the screen is a little bit fuzzy because it's like somebody out of focus, and you see the two images of the eagle, and they are sort of flapping around each other. So that is the principle of polarized light, how your left eyeglass and the right eyeglass have been in that same orientation. And the industry has already fixed. I'm not in the industry, so they know which one is the relative polarization for the left eye and for the right eye. Okay? Well, this is basically the same thing. This is basically the same thing. So, but now, let us now deal with nature. Namely, we already said that from the sun, it's not polarized because it has all possible orientation. The sun is like a furnace. Of course, it's more than a simple furnace in the house. And all the light coming out has all possible orientations coming. But when it comes through our sky, the light begins to interact with the molecules. Well, because we have atmosphere. Before the sunlight reached our Earth atmosphere, there was nothing. The light was just coming, whichever it was, and it was, in whichever orientation, unpolarized light coming. But when the light now comes and hits the molecule, you may have heard that molecules are made of atoms, and the atoms, they have a certain structure. Like water is does anybody know chemistry? Water is what? H something O. Does anybody remember what is? Thank you, H2O. What that means is it has one oxygen and two hydrogen, right? It has one oxygen and two hydrogen. And now, therefore, there are orientations where it is easy for the electric field to influence the electrons that are going around this H2O, around the hydrogen atom, around the oxygen atom. And it's a very complicated process. It's not something that you will say, ooh, I want to learn how they figure it out. Leave it to the scientists, the physicists who have been dealing with it. And so they say that as a result of the scattering, there is some orientation. But if you look in the longitudinal direction, if you look in the direction of, let's say that's where the sun is, then it is still unpolarized because there will be random orientations of these molecules. But when you look at an angle away from the original direction, let's call this the longitudinal direction. If you look away from it, then there is a difference. Why? Because the molecule has its own, the molecule becomes sort of like a polarizer. That if you have your electric field oscillating in the orthogonal direction to where my electrons are, no big deal. My electrons are not as excited as if you were now, let's say my electron are all going zoom, zoom, zoom down here, and then your electric field is in this direction, you're going to distort my orbit. Why? Because if this is the electric field and my electron is coming this way, it is attracted, But when it is now going this way, it's being pulled back. So instead of the original circular orbit, which was so nice for my molecule, now it is distorted. And so it no longer, it will now emit radiation, we call it. It will emit radiation. And the way it emits radiation now depends on your orientation of your original electric field coming in. So then this becomes partially polarized light. And then if you now look at way 90 degrees, it becomes polarized light. So this does not mean that there is a film strip. This only just says that as you look at the sky, there is a difference in the degree of polarization from sunset. In sunset, you will see it more or less, between the noon sky and the sunset sky. The noon sky, what we see basically is about 90 degrees. Are you following my picture? The sun, this is now, let's say, noon or 2 o'clock or 1 o'clock. The sun is shining. It is mostly blue sky. But when the sun is setting, you are sort of like a different orientation with the sunlight, and there is a difference. So anyway, you at least get the sense of it, not the actual mathematical formula associated with it, but you get the sense of this. Yeah, I mean, we just need to know that indeed the way the sunlight hits the nitrogen, oxygen, carbon dioxide, whatever, they all have their own set of directions that are preferred for the polarization. And it depends on whether you are in the direct light, line of sight, or you are a little bit at different angle. You will have different degrees of polarization. Okay. And now I want to end this quick thing with this nice picture of a butterfly. I have no idea what is this Heliconius sydno butterfly. Does anybody know what? Do you know? Are you a naturalist? All I know is a butterfly is a butterfly, but I didn't know there are some butterflies that actually have special polarization properties. Yeah. Anyway, here they show you a picture of the butterfly, and they now have one side where there is no filter and the other side where there's a Polaroid filter. And then they say, on this side, oh, it looks like very colorful, right? But these are now one side, yeah, this side is through a filter, and that filter shows that not as much light. What that means is that the light is polarized, sort of orthogonal to the polarization. In other words, the butterfly as a whole itself, not the whole wing, is not emitting light without polarization. The whole wing, different parts of the wing are emitting light with slightly different polarization. And then when I analyze it, when I put a filter, then I say, ooh, somehow I don't see the middle. I don't see these guys, these parts of the wings, which therefore means that these parts of the wing, they emit light that is polarized orthogonal to my filter. Do you follow? The fact that when I use a filter and then I see dark, that means that the source itself must have been polarized and must have been polarized orthogonal to mine. So it's interesting. But I think for you and me, I don't think my left hand is sending out light when it reflects, that is sending out light that is polarized in the, I think they are all randomly polarized. But the butterfly, this particular butterfly, Heliconius sydno, is interesting. Don't you find it interesting? Right? it's interesting that here it looks like, oh, very colorful, very nice. But then when I put a polarizer, onto it, then I find, oh, at a certain orientation, this is totally dark. Therefore, it says this is polarized light. Yeah, it's nice. Of course, I don't know whether this is true of all butterflies. You have to ask a naturalist, the people who spend all the time going around trying to look for new species. They will then say, oh yes, this kind of butterfly, yeah, it's very nice. But the other kind of butterfly, there's nothing special, all right? Okay, we are then done with electromagnetic waves. Any questions or comments? Okay, so now let's see. I will now go to the other guy. Where is my other one? Okay, now I will. Okay. Now, do you see this? We are on chapter 25 because you'll be doing a lab on optics. Okay. And now, optics, you already know enough, at least the kind of optics that we need. So again, we can go kind of quickly, but still, it's good to distinguish certain aspects of this. Now we already know about sound waves. Sound waves gives you wave front, right? You have a whatever, a pulsating sphere, it will send out sound waves. So you have a wave front, and each wave front is one wavelength next to each other. And then the further out you go, the sphere, the wave front, which would be in a sphere, will become larger and larger. But the intensity, of course, will go down as 1 over r squared. All right, so we all know this. We already learned it in the sound. So now if you have, let's say, a source of light, but let's say they still call it a pulsating sphere, but now let's say it's a source of light. Then, of course, when you are far away, it would be, the wavefront would be curved, right? Because they all came from the original source. And the original source, like the sun does not say, I know you are over there, therefore I will focus all of my light on you, and I will not send light anywhere else. The sun doesn't. You need a separate mirror to focus all of the light of the sun onto you, right? So what we have here is, let's say, the sun, and it is radiating. That's the word that we use. It's radiating light all over, and the wavefront is, of course, spherical, and this is the wavefront here, and this is the wavefront further down, and so on. But when you go far and far away, this wavefront becomes like a plane. When you're really very far away, then this curvature is so small that it becomes basically a plane. And then we now use the language of light rays, R-A-Y-S. And the light ray from a very distant source is all parallel. When you are close to the source, the light rays, they are radiating, so they are, not parallel. But when you are very far away, we will talk about light rays that are parallel, coming from the sun, coming from the moon. Okay. And now, one of the simplest thing that you already know is this thing called the law of reflection. If I have a mirror and leave it to the manufacturers, leave it to the experts to have different quality of mirrors and how to make a mirror, the thickness of the mirror, actually you have a glass and there's a certain thickness, and there are many technical questions that the manufacturers of a mirror, they have to do analysis and they have to hire engineers, but we are not in that business. It's their business to make sure that when I buy a mirror, that it is clean and easy to clean. Because if I have a mirror and if it's a little bit soiled, I ought to be able to just with a wipe or something or other, it becomes clean again. But if it is a lousy quality mirror, it's smudged by my hand, by my finger, and the more you try to do it, the more smudged it is. I wouldn't want to buy your mirror ever again, right? So, but we leave that all aside. There is a fundamental, namely, if I have an incident ray that came from the sun, that came from the ceiling, and it now comes onto this surface, which we call a mirror, it will be reflected. And then the thing that you already kind of know is that the angle of incidence, we call this theta I, the angle of incidence that it makes with the normal is equal to the angle of reflection. All right, so this is incident angle, this is reflection angle, and this is the normal. And now, actually, while we are at this, in the ancient days, they didn't have a glass manufacturer. How did they have mirrors? I mean, I'm just interested in asking. Have you ever wondered? Or you don't care? Have you ever wondered? Good. Shiny metal. In the old days, they don't have a glass, factory that manufactures a glass mirror. What they had are shiny metals, especially the soldiers with a shield and so on, right? And when you have a shiny metal, the surface is absolutely smooth and shiny, and you actually can see yourself in it. So that's how they were able to see the image. And the other thing is, if you have the water, if you have a basin where the water is still, the water has no ripples on it, you look down on that thing, you see your face. But important thing is that the water is clean and the water is still. All right. So in the old days, they do manage to make themselves, presentable in face, right? So the incident ray and the normal, these are the things, and they are in the same plane. Okay. And now there's the difference between, let's say, a smooth, like a metal or a glass, and the kind of wall. Let's say sometimes you have a wall that looks like it is shiny, but it is not. It looks like it is shiny, but it is not. And then you don't see a picture of yourself. Why? Because you really look down, with a microscope, you find that it is not smooth. It is bumpy, up and down and up and down and up and down. And so when you have a light ray coming that hits this part, it's reflected here. But when it gets hit this part, it gets reflected there. Therefore, what is reflected is not a parallel. You don't see a clear image, but a clean surface, really clean. Clean in the sense that there are no rough spots and it is really very, very smooth. Well, then you have a nice image. All right. and they call it specular reflection. I would then say spectacular reflection, but anyway, it's specular, right? And now there are many things that we already know about imaging. If you are in front of a mirror, assuming this is a nice mirror that is clean, right? Well, you all know that when I see the image, my right hand is in the image, the left hand. Just like right now, I have raised my left hand, but on the terminal, on the screen, it looks like it's the right side of my head, right? Isn't it? Do you see my left hand? I really raised up my left hand on my left, but the image you see on your screen, is it my left hand or my right hand? You can tell it is my left hand, but my left hand is on the right. Yeah. So you just have to recognize this, and sometimes people try to fool you. You know, these nowadays with photo op and all that. Sometimes people try to fool you, and when they fool you, they may not have remembered that what is left is now right, what is right is now left. So although it is easy to tell with, I guess it's easy to tell because you know how I'm sitting. But if you don't know how I'm sitting and somebody sees an image of a hand, they wouldn't know whether it is left or right. Anyway, be aware of that. The image has three properties. Of course, it's upright, because if I buy a big mirror like this and I stand in front of it, if the image I see is upside down, I say, wait a minute. Wouldn't you say, wait a minute? Now, have you been to I guess, I don't know if Disney World has it, but to a nice amusement park where there is a hall of mirrors? Yes. Have you been to some of those? And then when you're in there, sometimes you pass by a hallway of mirrors where suddenly you shrink in size. Have you have you been to those kind of fun? Huh? Yeah. And in fact, there are times, it's not easy to arrange it, but there are times when you walk by and you say, hey, I'm upside down. And your, your kids or your brothers or sisters would really have a great laugh and say, hoo, you're upside down. Later, we will see examples of mirrors that give you upside down images. But this is a plain mirror. If it's a plain, straight mirror, you will see exactly what you are, upright, and it will be the same size as you are, and the image is as far behind the mirror as you are in front of it. I mean, all these are obvious. We already know this. And have you ever seen an ambulance? Now, does the ambulance have the thing that says ambulance, AMBULANCE? Have you ever noticed? The word AMBULANCE is usually the mirror image. Why? Because you want it such that I am in front of you, I'm ahead of you, you are now coming behind me, and I look at my rear view mirror. What I see in the rear view mirror is ambulance in the correct, orientation. In other words, it is the mirror image that is painted on the ambulance front, so that when you now see it in my rear view mirror, what I see is AMBULANCE. You following what we are doing here? It's you see it all the time, but you don't realize it. Yeah, the actual painted letters on the ambulance, front of the ambulance, is the mirror image, so that when you now see it in my rear view mirror and I say, ooh, there is a, you know, and then there is something that says AMBULANCE in the normal way, then you say, ooh, I don't even try to figure out what it is. It actually says ambulance, and so I should move aside. All right. So these are the simple things that we are living with. And now you want to now use the simple light rays to figure out where is the image. I have this, this is a chess. This is a chess, what they call a pawn or a rook, right? I have a, is that called a rook? Anybody who plays chess? Yeah, it's called a rook, right? So I have a rook, yeah, in front, and I'm looking in the mirror. When I see the mirror is the light that was reflected from the top of the rook, it reached the mirror and then it came to my eye. But what I now see, as far as the eye is concerned, it seems to have come from over here, right? Because the light ray that comes into my eye came in this direction. So it looks like it came from here. So this is what you call a virtual image, because what you see is over there, whereas it actually is over here. All right. So that's also, we already know that. Even a child knows that. And they want to show you the geometry. It's very easy. If you go through, this is the angle of incidence, this is the angle of reflection, then it seems to have come from over here. And whatever is this angle, it is the same angle here, because you have now, this is theta, this now is complement of theta, and this is theta, that's theta, and this is complement of theta. So this just shows that the distance of the virtual image behind is the same as the distance in front. I mean, this is just trigonometry. We already know that. And now here is a very interesting, I should have downloaded from the a different picture of it, but it's interesting. They now want to know, how would I have a mirror that in fact enables you to see all of yourself? You're standing in front of this mirror. You want it such that you be able to see your own feet and the top of your head in front of a mirror. And now this looks like a, I don't know, an exercise, but actually is important for applications. In the gym, they have in the gym that we used to go to before pandemic, they have an exercise room with all the bicycles, and it doesn't have that many bicycles. Maybe it has 12 bicycles in there, right, in the range, but they have mirrors all over, so that when you peek into it, it looks like it's a big bicycle exercise room with many people all cycling. How do they do that? They have mirrors. But for a restaurant, for you know, the kind of public area, they cannot afford to have a mirror which is from the floor all the way up to the ceiling. Number one, it's too expensive, and number two, the cleaning lady will have to clean the floors, right? Especially in the restaurant, you have to clean the floor. People spill things all over, and the cleaning lady would easily crack the mirror. You got the idea? Therefore, in a real restaurant, they don't have this part of it as a mirror. They have this part as just simply a wall, whatever of the color that you have made for the rest of the room, right? And then over here is where you have a mirror. but then you will have the impression that actually it is the whole restaurant is now much bigger. Are you following my description? You get the grasp, right? Yeah. And if you go to a restaurant next time, especially those restaurants that are really not that big, but they want to give you the impression that they are the super big restaurant, what they do is they have already arranged the design so that you enter, you see the mirror here, the mirror there, and it looks like, wow, this is very impressive. There are so many customers and everybody's enjoying and toasting one another. But actually, it is not. It may be a third of what it seems to be, but you have the effect, the visual effect. And this one is just a trigonometry to figure out what if your height is this much. Let's say whatever is your height, they call it height, capital H. Whatever is your height, what must be the minimum length of this mirror? I'm rephrasing the question. The question here is what minimum height for her to see her full image. I rephrase it to say, what is the height or the length of this mirror so that you can see your feet and your head? And here they have enlarged it to say that the eye must, this mirror must be at least up to here so that you can see your head. All right, so this is trigonometry question, which if you have time, you can kind of work it out for yourself. And now the book has an interesting conceptual example. And again, it's interesting. You're in front of a mirror stand and they have two mirrors, 90 degrees, you notice, and you're sitting in front of it and you see three images. Have you been to those kind of fun places? No? Yeah, I mean, of course, you don't, you enjoy it and then after that you come out, you say, okay, bye-bye. Now here they are saying the reason is you have the two mirrors 90 degrees and you are here. Of course, there's one image and there's the other image. This image is of you because of this mirror, but then this image is of you because of this mirror, but there's a third image. And where is the third image? The third image involves two reflections. This image involves one image, one reflection. That's how you get to see your hair, your face, your ear, and so on. But the image 3 came from two reflections. Why? Because this person's this light ray got reflected here, and came out here. And this ray got reflected here, and came out. And they seem to have come from the third image. So it looks like you have now three persons consulting one another on Zoom. All right. So it's for the Hall of Mirrors, they purposely make all kinds of interesting, angles of mirrors so that you get the illusion. And now we want to come to tricks. Beyond the simple trick of plain mirrors, we want to have tricks involving spherical mirrors. Well, for spherical mirrors, they first say, imagine that I have indeed a spherical mirror, and I now take this piece of this sphere over here, and I now have this thing act as a mirror. Namely, all the light rays coming on this side of it will get reflected. Now, this is what you call a concave mirror. I now, instead of making a plane mirror, instead of making a flat, straight mirror, I make it curve. If I make it curve, in this way, it's called concave. If the inside surface of the spherical mirror is polished, it is a concave mirror. But if I now make it the other way, it is the outside, then it is convex. And they have remarkably different effects. When it was straight, it was easy to get a kind of effect that we already learned. We know. You get your image, and the only thing is you have to know what is left is now right, but you are still upright. But with concave, with convex, now you watch it. The law of reflection applies just as it does for a plane mirror, but you now have to see what it does to the different rays that come from your source. And we will be talking about a principal axis of this mirror, which is where the center of the curvature is. This is called the principal axis, and whether it is concave or whether it is convex, there is a principal axis because that's the center of this sphere. Okay? And now let us try this. If I have, let's say, a tree that's very far away, some distance away, and I have this concave mirror. Now this tree sends out, like the top of the tree or wherever part of the tree, it sends out rays. Well, there will be one ray which goes, let's say, over here at the top. When it reaches here, it will be reflected according to the law of reflection. And if you look at the normal to this sphere, the angle of incidence will be angle of reflection. So it will now come down. Right? Do you see it? That's the reflection. The law of reflection works. So it will come down this direction. Then you take the other guy. There's this ray that comes from the top of the tree, and it will hit this lower part of this concave mirror. And again, there's a normal to this, and there will be an angle of incidence, an angle of reflection. So it will come up, and it will now go through this point. This point is now the image point of this top of the tree. And the third ray is parallel to the principal axis. It will pass the center, it will come here, but then it will be reflected exactly back towards the center. And so therefore, the image of this, the top of the tree, or a third from the top of the tree, it will be exactly here. All right? Do you see? You can kind of begin to appreciate this light ray, how to follow the imaging by following the rays, right? R-A-Y-S. Okay, now we begin to introduce a concept. If I have parallel rays from a distant, very distant object, the tree was not quite so distant, but now this is really very, very far, then all the rays from that object are now parallel. All right? And if I have, let's say, a ray that's up here, it's coming parallel to the principal axis, it will now be reflected according to the law of reflection, and it will now come over here in this direction. Well, the ones that are below the principal axis but parallel, it will now be reflected and go through this thing called the focal point now. And then the ones that came in the along the principal axis, they came through the center of the curvature, and they will be reflected exactly back towards the center of the curvature. Therefore, the parallel rays from the sun, the parallel rays from a far distant object, will now all be brought to this focal point. And this is called the focal distance. Light rays near and parallel to the principal axis are reflected from the concave mirror and converge at the focal point F. All right, so there is a focus. There's a focus. The focal length is the distance between the focal point and the mirror. Okay. Now, the focal point of a concave mirror is halfway between the center and that. Namely, this distance is half of the curvature. The focal point is half of R. And rays that are close to the principal axis are called paraxial rays. But rays that are very far from it, they begin to be scattered in the sense that the ray that is over here, it will be reflected over here, and it will be reflected over here. So for those rays that are very far away from the principal axis, you get what is known as spherical aberration. Now, when you have camera, the lens is a sort of a spherical, a portion of the spherical lens, right? So you have a spherical lens, then there is generally a spherical aberration around, namely those light rays, the image of my bookcase or image of my this, when I really have a very sharp camera lens, the manufacturers have to minimize this spherical aberration. And the way you minimize the spherical aberration is not to have too big a lens. Because if you have a very big lens, you have a lens that is, like this big, you get spherical aberration. That's why when you have one of these Nikon or whatever your camera is, nowadays people don't buy these, only professionals do. Nowadays you just rely on your cell phone. But for those, the lens usually is not big. And if it is not big, you don't have this issue. Do you follow what I'm talking about, or what the book is telling us? When you have a big lens, then they will collect the image. They're from the same image, they are from the same source, but now there will be what they call aberration. Namely, they don't all bring down to the same focal point. Instead, they will be spread all over. Okay. And now this is an example of a instrument where what they want to do is, you have the sunlight. You now want to focus the sunlight on some pipe so that you warm up the pipe. And so what you do now is you have this, but now you don't mind that there is spherical aberration because you're not looking for an image of the sun by doing this. Instead, what you want is for the light, the heat or the light from the sun to be focused, let's say, mostly on this pipe, although there is some spherical aberration, but you're not looking at the image of the sun through this pipe. Anyway, these are the applications that they have, and there will be other applications. All right, now we already have a concave mirror. Now we want to have convex mirror. When you have a convex mirror, this is called convex, yeah? When you have a convex mirror, a parallel ray that comes this way will be reflected, and it will be reflected upwards. Whereas the concave mirror, it was reflected downward. This convex mirror is reflected upward. Therefore, it appears to come from this focal point. The ray that is exactly along the principal axis will be reflected so that it seems to come from the center, and the parallel ray that is below the principal axis, it will be reflected over here, and it seems to have come from here. So now this is the focal point, but now this focal point becomes virtual because the light did not really come from here. It seems to have come from here. So this is virtual, and this focal length now is negative. The engineers will now give a convention, a mathematical convention, and they'll say this convex mirror has negative focal length. All right? I mean, it makes sense. What was over there is positive, what's over there is negative, because positive means it really did focus through that point. And when it's negative, it means it seems like to have come. It's like it's behind the mirror. Okay, now we want to look at the interesting effect of a concave mirror. You have an object that is over here between the center of this concave mirror and the focal point. Remember, the focal length is half the radius of this concave mirror, but now you place an object that is in between. And now you want to say, where is the image of this object? Well, we now do the analysis and we say, okay, let the head of this object, the top of this object, send a ray which is parallel to the axis, and it will then be reflected through the focal point in this direction. All right, so I have now drawn one ray. Then next I say, how about from this top of this object, I sent a ray which was going through the focal point. Well, if I send a ray through the focal point, when it gets here, it will be reflected so that it will now come back parallel to the principal axis. All right, so I now have a second ray from the top of my object that will now have this path. And then lastly, I now say, what if I have a ray that was directed upward as if it came from the center? If I have a path that went up towards the mirror as if it came from the center, of course it will be reflected directly back to this direction. So now I have three rays. And if I now put the three rays together, the place where they converge is over here. Are you following this? We drew the first ray, we drew the second ray, and we drew the third ray, and it's clear that they will intersect not over here, but somewhere to the left. And now, this is now doing the actual drawing to scale, and you see, well, the rays will converge over here so that the top of this tree is now inverted. And of course, the bottom of the tree would still be in this direction here. So the image, well, this is the reversibility. If I have the real guy Oh, no, actually, no, the picture is reverse. Yeah, sorry, I animated it the wrong way. Sorry. Originally, we were doing this. So don't, I animated it in the wrong order. Sorry about that. Sometimes when you're animating, what happens is this is the real tree and its rays converge over here so that now this is the real image. So a real object gives you a real image, except that the image is now upside down. And now this principle of reversibility is, supposing now I have the real image this way, where's the, I mean the real object this way, where's the image? You reverse everything and the image is over here. So you can substitute, namely the image is now upside down and the image is bigger depending on where you are. If you are within this, then the image is bigger. But if, let's say, your object is really far away from the center and from the focus, then the image will be inside and it will still be inverted. They are reversible, but they are always inverted. So if I want to have a hall of mirrors to make you feel, joyful, what I do is, instead of having a plain mirror, I actually have a curved mirror, and I make it such that you actually walk, you walk within the, let's say, within the curvature. Then what you find is your image is bigger but inverted. Or I could arrange for my curvature to be such that you are walking over here. You're walking over here. Then you will be shrunken and upside down. Are you following what I'm saying? Namely, with a concave mirror, you always get real image, but depending on your location in front of the mirror, how far away or how far within the radius of this curvature you can have, when you are, let's say, when this concave mirror has a very large what you call radius of curvature, then you'll be walking in a, let's say, lane where you are within this. And if you're walking within this, the image you see, you're bigger and upside. But if the curvature of this thing is smaller and you are walking now down the hallway and the curvature is smaller, then what you find is that you will be now walking here and you will see yourself upside down but smaller. It's whatever you are standing up, then the image is upside down and smaller. Well, that kind of fun you will only appreciate when you're actually there. Any questions or comments? Yeah, and I don't know what exactly the lab experiment you have, but it will be involving mirrors. So, and now, well, yeah, this is repeating what I just said, that if you are oh, now this is more. If you go in between the focal point, namely you are really much closer, then the image is virtual. And the image is now the same orientation but bigger. You remember, for the other cases, it was always inverted. depending on whether you are walking far away from the center of curvature or you are between curvature and the focal point. Now this is going even further, closer than the focal point. Then what happens is the image is virtual and bigger. I mean, those are the interesting effects that as you walk along the hall, you find yourself bigger, smaller, upside down, and you get a lot of laughs out of it. Oh, yes. Here it is not just the hall of mirrors. I guess everybody, when you want to do makeup and you want to make sure that you have everything put together, then indeed you are making use of a spherical mirror, and indeed you are putting it close to you. You see, you are closer than the focal point, and then you see a magnified image of your eye. So this is indeed not just simply for fun. You do it because you want to be sure that you are good, presentable. Okay, now what is this one? This one is I don't know what this one is for. Now let's come to convex mirror. And that for driving is a very important thing to have convex mirror. And for convex mirror, the thing is it's always virtual because all these rays, they will always seem to diverge by reflection. And therefore, they will always seem to come from a virtual source, and it will always be smaller. And that is why when you are driving and you're relying on the side view mirror, the side view mirror, the image of the side view mirror, you see a car, it looks like it is far away, but actually it is not as far away as you think it was. Why? Because the actual car is of this size, you know, but the image you see is smaller. And when you see it smaller, it's sort of like, ooh, it is further away. So all these side view mirror, the car manufacturers will always say, the images, beware that the image, that they are closer than you think. You understand what they are saying, right? It looks smaller, therefore you think that it is further away, but actually it is closer than you think. So that's what this lesson from this is. You draw all these, rays, and then you discover for convex mirror, it's always virtual and it's always shrunken, but do not therefore think that the car is very far away. And you have to learn by experience when it is that you should be aware that there's a car almost by your side. Okay, it's diminished in size and upright, yeah. Okay, so we have now a formula just to say that F is the focal length, D sub 0 or O is the object distance, D sub I is the image distance, and M is the magnification. And now the engineers, the optical engineers, they have a fundamental formula. It's called mirror equation. And the fundamental formula is 1 over D0 plus 1 over Di equal to 1 over F. F being the focal length, D0 being where you place your object relative to the mirror, and where Di is now the image. And this is the algebraic equation. Whether you have a concave, whether you have a convex, well, then for a convex, the equation here, F is negative. And whether you place the object D, where it is from the mirror, it is DO, the object, and DI may be positive or negative depending on where you are relative to the focal point and the center. So this is then the basic mirror equation. And probably upstairs when you do the lab, they will ask you to make measurements and then to figure out where is the image distance by using this equation. All right, that is the basic equation. The only thing you have to be careful is the algebra. For a concave mirror, this little f is positive. For a convex mirror, this focal length is negative, and in front of the mirror, this is positive, and if this is a virtual image, is negative, and so on. And for many of these applications, important question is, what is the magnification? You want to know, is this magnified or diminished? What is HI, namely the image height, versus the original height? And that is related to what is the distance, di over d0. And the minus sign is just to remind yourself that if it is inverted, it's negative. If it is positive, that means that it was still upright. Right? So these are the two equations that would be necessary for all optical analysis. Am I going too fast? Okay, all right, yeah. Okay, so now, well, this is just an application. Even though it's for engineers, since we have time, we can just quickly say, you are told that there's a convex mirror from an object that is 66 centimeters in front of the mirror. The focal length of the mirror is negative 46 centimeters. When they say negative, that means that it's convex. When they tell you it is convex, then you better remember that the focal length is negative. And now they say, where is the image and the magnification? Well, the mirror equation is 1 over f equal to 1 over di plus 1 over di. Therefore, algebraically, you want to know where is the image. You say 1 over di is 1 over f minus 1 over di. No, this one is again wrong. Oh, I keep seeing all these. Whoever does the Wiley Plus slides, somebody should tell them. This should be D0, the object. And so the focal length is negative 46, and then it is minus 1 over D object, which is 66 centimeters. And when you do this algebra, it now gives you negative 0.037 inverse centimeter. Therefore, di is negative 27 centimeters. That means that the image is virtual. That means that the image is virtual. And now you say, what is the magnification? It is negative di over d object, and di was, image was negative, virtual, so it's negative 27. And then the object was 66 centimeters. Therefore, the magnification is 0.41. What that means is you're shrunken. The original object is a certain height, whatever the height was. The image by this convex mirror, the image is actually shrunken, and it's shrunken 40%. It's only 40% of your original height. All right? Are you okay with this? This actually is a very simple application, and because I called it for engineers, I did not even check. But now I see you better not be fooled. This is the zero object. Okay, now, And then this is the convention for concave mirror, positive, convex mirror, negative. An object, if it is in front, it is plus. If it is behind, it's negative. Image plus, if it is a real image. If it's virtual image, is minus. And M is positive for upright object. And M is negative for inverted object. Oops. So I guess, gee, we have gone very fast. We have gone very fast. I didn't prepare for chapter 26, or did I? Let me see. Any questions while we are at this? It would be, this is chapter 25, it should be 26. No, I didn't prepare chapter 26. Sorry, I didn't realize I could go that fast. All right, so we'll just say any questions of general or particular of any issue. Oh, by the way, homework 24 is up. Yeah, okay, that's a good question. The question is, what will be on the test number 2? I haven't yet made test 2, but it will be on those that were beyond induction. Because did we not do induction already for test 1? Or not yet? I get confused myself. Oh, well, then certainly. But we did do Coulomb law and the electric field, right? So we have to do chapter 20. Is it 22? 20. There's no 23. Well, anyway, it will be on magnetic field. It will be on Ampere's law, because we know enough about the electric field, the force, but now we need to learn about this Lorentz force. And with this Lorentz force, in the presence of electric field and magnetic field, the force is Q, whatever is your charge, times E, the electric field, plus V cross B. That is the Lorentz force. And as a result of that Lorentz force, there's a force on the wire due to external magnetic field. And you can work it out to be basically IL cross B, the direction of your current, the length of the wire, vector product with the magnetic field. So you need to learn about what is the force on the wire as a result of an external magnetic field. And then we have this whole chapter on electromagnetic induction. You have to be responsible for that, because there are many concepts that are involved. The electromotive induction, and what is the not emotional, what is the motional EMF? Due to the fact that you are pulling this through a magnetic field, you are now inducing a current. If there is indeed a circuit, you will have induced a current. Even if there is no circuit, there is still motional EMF. Even if you did not close the circuit so that there's no current flowing, the fact that you are moving this rod, or this rod in the given magnetic field, the fact that you are moving that, there already is a motional EMF, and the magnitude of it is VLB, the velocity with which you are that rod is moving. L is the length of this rod cross B. So know those basic formulas, and then you'll be able to say, oh, therefore I know what is the motional EMF. I know what is the induced EMF when you have a current flowing in this rod, in this loop. And when there's a current flowing through this loop, oh, that is the EMF that is VLB or ILB. So it is, and the actual final formula that surpasses all is this Faraday's law, because Faraday's law now says that the induced EMF, the actual induced EMF due to this motion of your loop, of your wire through this magnetic field is negative n, the number of loops, times the rate of change of the magnetic flux through this loop. And that is the fundamental Faraday's law for the effect. And as a result of that, there are many, applications. And there's also this transformer that we all need, because we need to step up the voltage. And in order to transform it, you now have, did we not do inductance? I forgot. Did we not do inductance? Oh, we didn't do inductance? Ooh, what did I do? I thought I did. No, can somebody correct me? Are you sure I didn't do inductance? Boy, I'm getting so old. Yeah, you better check. I thought we did inductance. Because that's part of the transformer, and I think we did do transformer. Is somebody checking now? Yeah, that's what I thought. We did. But anyway, since people ask what would be on test 2, yes, we talked about electromagnetic induction, and transformer works on this Faraday's law of induction. So we had the discussion on how you can step it up, because the magnetic flux goes through the magnet, and you have a primary coil, and because you have your current that is now changing inside the primary coil, it now induces the magnetic flux, and the magnetic field now will change, and it will go through the secondary coil. And because the magnetic field is changing on the secondary coil will now have an induced current, and that's what you get your transformer either at a higher potential or at a lower potential. So electromagnetic induction will be a big question on test 2. But test 2 will also have things on the electromagnetic waves, which are the simple aspects, application aspects on the AM, FM radio, the wavelength and the frequency and the Doppler effect, which is important. So the induction, electromagnetic induction, the Lorentz force, I'm sort of giving you overall picture. The Lorentz force, the electromagnetic induction, including transformers and inductance, and then the electromagnetic waves, and maybe some simple questions from optics, although it's just simple questions, not detailed questions, because you're not an optical engineer. All right, but I will know more by maybe, what is chapter 25? Yeah, but chapter 25 is really simple aspects. So, you know, it's not something that you have to scratch your head and say, "Woo, what should I learn?" Okay. Chapter 25 is really very simple because we are not going to be yet going into index of refraction, rainbow, and all that, because I think that really belongs in optics, the course on optics. And chapter 26, what is chapter 26? No, it's not on it. Okay. Any other questions? Well, we have 3 minutes, ask more questions. Don't be shy. Okay, so if there are no questions, we can stop recording. Let me get now.